All right, let's jump right in. When you think about public policy, things like criminal justice, public health, we're talking about decisions that literally shape millions of lives. But how are those decisions actually made? Well, more and more, they're driven by data. So today, we're going to take a journey into the statistical toolbox that researchers use to figure out what really works and what doesn't. Okay, so at the very heart of all of this is this one crucial split. On one side, you have prediction. That's all about forecasting what's going to happen, asking what's the chance this person will re-offend. But on the other side, you have causation. That's about understanding why. Did our new program actually cause the drop in reoffenses? They sound pretty similar, right? But believe me, getting from one to the other is the entire game. And this example just perfectly lays out the challenge. It is so easy to see two things happening at the same time. A new policy gets launched, crime rates go down, and just assume one caused the other. But what if the economy got better during that same time? Or what if a different policy was also rolled out? How can you possibly prove it was your specific thing that made the difference? To answer that question, we have to start with the foundational tools. This is all about learning how to isolate the signal, the effect of the policy, from all the other random noise that's happening out there in the world. So our first and maybe most important tool is something called regression. Now, the core idea here isn't just about drawing a line through a bunch of data points. In policy, the real magic of regression is its ability to control for all those other factors. It lets us ask a really specific question. What is the true effect of this one single thing if we could just magically hold everything else, like a person's age, their income, their background, exactly the same? But what happens when the outcome you care about isn't a number, but a simple yes or no? Did this person get rearrested? It's either yes or no. That's where a special tool called logistic regression comes into play. It lets us calculate the probability of that yes, isolating the impact of the diversion program while mathematically accounting for the fact that, younger people or people with more priors might have a totally different baseline risk to begin with. Let's look at another really common situation. Say we pull the data and we see that Judge A sets an average bail of $5,000, but Judge B's average is $6,500. On the surface, it looks like one judge is just way tougher than the other. But is that difference actually real? This is the exact question that something called hypothesis testing is built to answer. It gives us a formal way to figure out if that $1,500 difference we're seeing is a genuine, statistically significant pattern, or if it's something that could have just happened by pure chance, based on the random mix of cases each judge happened to see that month. It helps us separate a real systemic issue from just random luck. Okay, so let's build on that foundation, because with the rise of machine learning, we now have these incredibly powerful predictive tools. But when we start applying them to public policy, we slam right into a whole new set of really thorny ethical challenges. And here is where things get really complicated. A typical machine learning model might just try to be as accurate as possible overall. But in policy, the kind of mistake it makes matters immensely. The human cost of an error can be totally different depending on which way that error goes. This chart is called a confusion matrix, and it is perfect for seeing this dilemma. Just imagine a parole algorithm. A false positive means the model says someone is a risk, but they actually weren't. That person is denied parole unfairly. A false negative is the opposite. The model says they're safe, but they're released and go on to harm someone. So, which error is worse? There is no easy answer to that question. And this quote just hits the nail on the head. When you hear people debating algorithmic fairness in the justice system, they're not really arguing about the model's overall accuracy score. They are really arguing about the trade-offs between these two types of mistakes, the ones in those highlighted off-diagonal squares. So, this brings us to the final tier, which you might call the gold standard of policy analysis. We've talked about controlling for things, we've talked about understanding errors. Now let's get into the methods researchers use to actually prove that a policy caused a specific result. This is the ultimate objective. It's called causal inference. It's a whole set of advanced techniques designed to get us as close as we possibly can to the certainty of a randomized scientific experiment, but by using real-world data that's already out there. So one of the most powerful and honestly elegant methods is called difference in differences. The logic is actually beautifully simple. First, you find a group that got the new policy. That's your treatment group. Then you find a very similar group that didn't. And here's the key. You track both of them before and after the policy. And you don't just compare where they ended up, you compare the change in their outcomes. This is a perfect real-world example. Let's say one county decides to eliminate cash bail. And hey, its jail populations drops. That's great. But what if jail populations were already dropping everywhere in the state at that time? Well, by comparing that county's change to the change in a neighboring, similar county over the exact same period, we can isolate the true effect of just the bail reform itself. Now, here's another really clever approach. It's called regression discontinuity. See, sometimes policies have these sharp, kind of arbitrary lines that decide who gets something and who doesn't. This method takes full advantage of that. For instance, imagine a law that gives a massive sentence enhancement to anyone convicted of their third felony. Researchers can argue that people with exactly 2 priors are pretty much identical to people with exactly 3 priors. I mean, the only real difference is that one of them just happened to cross that arbitrary line. So by comparing the outcomes of people right on either side of that cutoff, we can isolate the causal impact of that harsher law. So why did we just walk through all of this? Well, because understanding these methods isn't just some academic exercise. It's about making sure that the policies that shape our society are built on actual evidence, not just on hunches or assumptions. Just think about the journey we just took. We started with the simple act of just seeing a pattern in some data. Then, we leveled up and learned how to use regression to control for all the noise. From there, we had to confront the heavy ethical weight of our model's mistakes. And finally, we landed on these powerful methods that can actually start to prove causation. Every single step adds another crucial layer of rigor and, frankly, responsibility. And that really leaves us with this final massive question. Because, it's one thing to build a model that is statistically correct. It's another thing entirely to build one that is fair, that is equitable, and that is just. And as data becomes the absolute foundation of public policy, bridging that gap, well, that's probably the most important challenge of all.